Hi, thank you for being here today. Last session, so thank you very much for sticking it out and making it to the very end. My name's Andrew-Shieh. I run the operations team at SmugMug, and today I'm going to talk about how we migrated our web serving and entire database infrastructure into AWS and what we learned in the process. I'll be happy to take any questions during the talk or afterwards. We can make it a little informal since this is the very last talk here at reInvent. So SmugMug, who are we? You've probably heard of us from some of the AWS earlier talks and like our keynote video, things like that. Anyway, we're a team of over 100 superheroes, as you see in this photo here, who run a premium photo and video sharing service for millions of our customers, ranging anywhere from amateur photographers, hobbyists, families, and up to pro photographers who run their businesses through us. As a premium service rather than a free one, the main challenge we face is how to serve our customers very high needs for serving photos very quickly. We serve billions of photos and videos, and we have to get them out as fast as possible to provide them with the best possible experience. So you may have heard of us from the new SmugMug, which we released in July. And also, we have a very popular camera app called Camera Awesome, which is out for iOS and recently for Android. So that's us. In the early days of SmugMug, well, we're a bootstrap company, which means that all the money that the company earned went back into it. And that kind of bootstrap growth leads to interesting problems, which I'll talk about. Part of this complexity is having multiple self-managed data center cages. So when you grow in that fashion, you rent out a small data center cage, and then you grow, you might get a different cage, and you have all these things to manage. The other part about bootstrap growth is that you end up with lots of different server types, and building over the years, you just obtain this as time goes on. You get better servers, but you keep the old ones around, and it becomes complicated. And finally, since SmugMug is a photo site, there were a huge number of disks involved, and those are just growing and growing and growing. And the worst part about all this is we have employees like Strongbad here spending valuable time just working in data center cages, doing work like racking and networking. And that's not really what our business focus is. So data center fantasy is something I call what we see at conferences a lot of the times. We see Google, Facebook, Yahoo. They show off these great custom data center designs where everything's perfectly laid out. All their cages look great. Their cabling looks something like this. So that's this great model. I really like it because I used to be a civil engineer, so I'm really impressed by all their construction. And so they do a great job. So this is actually a photo I took of a Cray supercomputer, and these are actually cooling tubes of floor inert. Some goes in the hot side and comes out the cold side, or goes in the other way. But what if you're not big enough for an entire data center? What if you don't have all this great technology to build your own data center? Well, what you end up is you have data center reality. And this is what data center reality can look like. This is an actual photo from one of our data center cages. Growing a data center gradually like we did, it means you accumulate a mass of physical debt. Like I said before, you gain all this hardware that you don't really want to take care of. So a lot of times, you leave old hardware lying around, and you have to work on a lot of obscure knowledge. So as an example of this, one day I spent 3 hours just trying to figure out which Java JVMs I needed to run on a variety of these Sun lights out management consoles. So things like that, figuring out port settings for accessing the consoles. It's not really a good use of my time. It's not good use of anyone else's time either. Along with all this physical work, there's things like negotiating contracts, organizing what you order, troubleshooting them, procurement, racking, cabling, formatting, building, and then when you're done with it, you got to retire and liquidate it and make sure you close out all the contracts. So that's really not our business. Our business is in data centers. And there's experience of being on call. Basically having the data center requires our ops employees to live right next to the data center or within a reasonable distance. And that's not really ideal for a lot of our employees. One particularly ugly scenario we ran into very early on was that we got basically kicked out of a data center just because there was this up-and-coming company, begins with a Y, that decided we need more power. So the data center company told us, we're cutting off your power in 1 week. So there you go. And so the company ended up taking some station wagons and carefully taking out disks and putting them in redundant station wagons and carrying them to new cage. So that's data center reality. It's not pretty, but it can make for nice photos. So SmugMug really we love AWS. We're a very early adopter of S3. We started in 2006. We got a cold call from somebody at Amazon just asking our CEO, are you interested in this product? And I think he quoted some number, and he's like, no, it's a little too high. And they called back in a few hours and said, here's a lower number. Are you interested? Yeah, that's great. So you may have heard that story at last year's reInvent, but over the years we moved our rendering, our uploading, archiving, payments, permissions, email, and a lot more into S3, into AWS, and of course all of our photos in S3. But what was really stopping us from moving the rest of the infrastructure was that there was no ultra-high performance I/O. And that's a lot of what I'm going to discuss here is how we came about getting our performance up there and how we moved all the rest of the systems into AWS. So this photo is actually relevant here because we built a system called Skynet before there was auto-scaling. So a few simple geographic diagrams here. We had, in 2006 was the time we moved to S3 again. So we had all of our web hosts. There was no EC2 back then, so all there was for AWS was S3. And we stored our photos there. Eventually, we trusted enough to store all the photos. But everything else was stuck in our Silicon Valley data centers. And you saw the pictures of how that turned out. As of 2011, we moved all of our image serving and image processing into AWS, into EC2 and some other systems there. And what was left in our Silicon Valley data centers were our web serving and database, which includes like load balancing and other assorted infrastructure. And that's what we were looking at here in terms of moving 100% in. So there's a little transition state that we had, which I'll talk about a little more in detail later, which was before we had any kind of high performance I/O, we thought about, we do really want to move more into AWS. If we can get a data center up closer to US East, we can run a direct connect in, and we can run just the hardware that we can't get in EC2 out of our data center there. So that was a good idea. Managing hardware from 3,000 miles away isn't all that great, but it's doable. And again, I'll talk a little more about that. And today, what we have is nothing in our data center, which has been a dream of ours for a very long time, and everything's in AWS. So how did we get there? And that's what we're here to see. So in our database hardware, we've always been on the cutting edge of IOs. We started early on running our MySQL on spinning disks and RAIDs. It was a pretty common configuration back in the early 2000s, just maxing out your spindles, maxing out RAID. From about 2006 to 2010, we bought these like Sun and future Oracle storage appliances, which at the time were like, wow, these are great. They use SSDs, which at the time were ridiculously expensive, but they use SSDs in a smart way along with disks for caching. And those provided pretty good cutting-edge performance for a few years, but again, over time, they lost to what we finally ended up building, which were RAIDs full of 24 SSDs. And those were very speedy and had some interesting characteristics, which we'll go into. And finally, for database I/O, we ended up using high-1.4 extra-large instances. We were very, very happy with them. And the main reason we found them to be an improvement over our custom-built hardware, well, our custom-built hardware was very obscure. We didn't really have anyone to follow. There aren't too many people who develop this kind of hardware and run the kind of SSDs we do. So, we have a very unique configuration. We custom build them, and that leads to some problems where you find little bugs or you have difficulty upgrading something you want to upgrade because of, like, say, a driver problem or something related. And there's a lot of obscure SSD and RAID problems that you can deal with, like, trim and things like that. So they're very difficult to upgrade and somewhat unreliable. The worst issue we encountered with them was one time we discovered, well, this is a bug which I think was pretty well known, but there are some Crucial and Micron SSDs that after a certain amount of uptime, they'd simply stop working. So, wow, that doesn't really happen with a regular spinning disk, and you don't expect it. Luckily, we knew about it in advance, but you can imagine how catastrophic that would be on a RAID system if all of your disks fail at the exact same time. Overall, on the high 1.4 extra large, we found that the database I/O performance was approximately comparable to our SSD RAIDs built with 8 SSDs in a RAID 10. So very good compared to the 24 disk. It's generally faster in random writes and a little slower in random reads, but this is great for our database needs. We didn't need like super cutting edge simply because SSDs were so amazingly fast at random I/O. And the best feature that I've seen on the high 1.4 extra large is that their failure rate is extremely low. We think of EC2 instances as things that are disposable and they can go away at any time, but so can regular hardware. We kind of think of it differently, but with these, we're getting less than 3% failure per year. That's better than any standard hardware that I know of. So whatever architecture is behind that, we don't know, but it's actually a very good design and probably the most reliable instance that we deal with. The other big win we saw in moving over was Amazon VPC. We could simply map our entire internal and external network security that we use in data centers straight into AWS. So very easy. So now I'm going to talk about a zero downtime move. What does zero downtime mean, actually? What do other companies do when they move their services around? I have a couple examples here. So this is a service I use pretty frequently. It's like a RSS newsreader kind of service, and they recently had a big move. So all they said was, we're not available. It turned out to be, I think they predicted a 48-hour move, and it ended up taking 3 days. So for 3 days, all they could deliver was they could deliver a map and some random cat photos, and that was their way of expressing downtime. So, am I going to complain about that? Not really. It's a free site, and they can do what they want, and I don't don't pay for it, so maybe it's not very critical for them to be up all the time. So SmugMug can't do the same. We have paying customers, we have families who depend on us to see like baby photos, and we have businesses that depend on us to serve their clients. So that just doesn't work for us. Here's another example. This is from a very popular, mostly free photo sharing site that's ad-supported. So they recently did a data center move, and they originally planned like an 8-hour downtime, ended up being around 9 hours. So, pretty good, but during this time, they had none of their photos viewable or browsable. So anyone who embedded their photos, so a common use of their site is, you use them to store photos that you embed on your blog or any other site. So not only was their site down, but all of their photo serving was down, which means that all of their, if you embed your photos from them, they simply weren't available for 8 hours. We didn't want that either. This site tried to make it fun by having some social networking stuff around what you're doing during the downtime, but we don't want that. It's paid service, and we think our customers deserve better. So a zero downtime move. How do you do zero downtime? Well, that's what I'm talking about here. And some of the things that help a lot, so AWS, wow, we can duplicate our resources. So that the previous two examples, neither of those two were cloud hosted, which means that if they wanted to have duplicate hardware anywhere, they would have to pay for it and go through all the trouble of buying it, liquidating it, and doing whatever they need for setup and takedown. That's a huge amount of overhead. And being in AWS, it means that you only pay for what you use, and you can provision quickly, take things down quickly. And the other big parts of the move are simply planning and testing. You have to do a lot of planning and testing. Once you've managed all the resources that AWS offers, well, you can do it. Some of the major changes we did post-move, so we talked about moving from our SSD hardware to high 1.4 extra large, and a big part of our change was also replacing our hardware load balancers, some F5s that we called Ferraris, because that's about how much they cost, and turning them into elastic load balancer. And behind the ELBs, we have a layer of HA proxy, and what that does is it gives us fine-grained traffic control. We can distribute traffic to different clusters and really have the exact kind of control over the web traffic that we want. And the one change we had to put into our HA proxy layer was being able to handle dynamic configuration of servers. Obviously, we going from a static list of servers behind our clusters to auto-scaling one. And finally, we're making a transition out of a Memcache product called Membase and into Elasticache, which we later ran into some problems with and used EC2, Memcache on EC2. Some of the big requirements we had for moving, so a read-only mode is really critical because there'll be some time when you want to test, but you don't want to write anything to your databases. You don't want any write traffic going to your site. In our case, browsing and being able to view your photos is maybe 80 to 90% of the business. So a read-only site mode only takes down like new uploads and a little bit of like private photo traffic. So read-only site mode is really important if you want to be able to move. And we can still consider that zero downtime because it's something you can plan and announce to your users in advance. Traffic control allowed us to shadow all of our traffic into our AWS test clusters. So what that means is we can pick some of our traffic, send it over, and it has no impact on our production load. This lets you say, if you want to test a certain amount of load, if you want to run, what we did was run all of our bots through there. It lets you test your traffic without any impact and have an actual real-world traffic scenario and see how your new test clusters respond. Finally, cross-country MySQL replication is very key here since we're moving our databases. And the way you set this up is the same as any other replication. MySQL replication is very simple. It's just sending a file over. The only thing you have to do there is calculate how much traffic your relay logs generate and make sure you have enough bandwidth to support however many databases you plan to replicate. And there's some tricks in there, but it's relatively simple. So the way we started initially doing some testing is we'd have some maintenance periods where we'd actually move our read-only traffic over. So the shadow traffic provides some degree of control, but some things we can only test by actually sending live traffic over there. And the reason we did it read-only was because this just being read-only prevents us from having to do database switchovers, which are moderate hassle there. So doing these read-only tests, we'd iterate on them. We'd do them every week during our maintenance periods. And those were extremely helpful in getting out some of the bugs that we discovered only by running at scale. Full-scale read-write testing is very difficult. Again, changing your read-write into a new location and then changing it back requires a lot of database switching. So we tried to avoid that and only restricted read-write testing to actual test-only clusters. One thing we found out was that we're always aware of some AWS limits. You probably know about some that are well documented, but there's a lot that are kind of obscure. We know about some like packet per second limits. We know like the API wheels that are hitting limits there. So you have to be aware of some of these limits, and for some of them you can actually talk to your account manager or support and get them increased. Especially if you're making a big change like this, you should talk to them in advance to make sure they have whatever capacity you plan on bringing up. It's not really something you want to wait for the last moment on. The other good source of finding the AWS limits is Trusted Advisor, which I think currently lists a good portion of them. But I don't believe that existed when we were doing this. Having a rollback plan is critical, of course. This is a very risky change. You're making a lot of changes at once, and if you have a rollback plan, you can insulate against a lot of the problems if you have something catastrophic happen. So making the switch. So our CEO called this the biggest and scariest engineering change we've made in the company's history. So, wow, but it's actually only a few steps, even though it's from internally we see it as very scary, but it's only a few steps to do it. So the first step we took was we went read-only. I've talked about how going read-only allows us to make changes a lot easier. Prior to this, we actually scaled up some of our clusters very large. Of course, you want to scale up to larger than you think they'll be. Things like ELBs you need to pre-warm. In our clusters, we have to get to a size that we think will be enough to handle whatever production traffic we get during our maintenance. We used a tool called MHA to reassign our MySQL masters and all of their replication clusters, and that was about a 30-minute process. And finally, to make the switch happen, we pointed our DNS and our CDN providers over to the ELBs. Next step in switching, a lot of testing. So we're in read-only mode, and just like the previous tests, we send our QA on it. They look at it, find any bugs, and that's all good. So I think in our case, that was about 60 minutes of read-only time. And then we went read-write. We checked all our databases, we went read-write, and saw what happened. So this is the really tricky part, because you're testing something that you actually haven't tested in the real world. We've tested it at small scale. We know how it behaves in our old data centers. We don't know exactly how it behaves in AWS. So luckily, this is late at night. We discovered some bugs at this step. And that's kind of inevitable because these changes, you can't really track every single thing down. In our case, the bug we ran into, the major one, was we had a provider which used whitelists that allowed certain IP addresses in, and of course this is not in our code at all. It's in our provider's code, so we didn't catch that. But it was easy. We made a call late at night and woke them up and got them to whitelist our new IP addresses. So bugs like that can come up, but hopefully not catastrophic ones. So MHA, what's that? So MHA is a tool it's developed by an engineer at a Japanese company called DNA, and I think he's at Facebook now, running MySQL there. Anyway, it's a very high quality tool that is used to reassign masters and all the replication clusters. And the tricky part that it handles is it'll make sure all of your replicas are in proper sync. So this is perfect for us. Previously, manual failover in MySQL, it would take us about 15 to 30 minutes if all went well, and pretty much only 2 of us knew enough to do that. So 15 to 30 minutes might be acceptable if you only have 1 or 2 clusters, but in our case, we were changing over more than 10 clusters. So being able to make this conversion to that many clusters in 30 minutes was much better than, say, taking 6 hours. One problem with this kind of automation is it's automation of a rare event. That has really bitten a lot of companies in the past. So you have to be very careful if you're trying to automate rare events. When you're automating frequent events, you get them tested all the time. But automating rare events, like, say, a database failure, is very, very dangerous, and you have to be very confident in your tools. There's been a large number of providers who've been bitten by this problem, and it's not good when you have some kind of automation failure that you don't completely understand. So in our case, it worked out fine, but you just have to do your research carefully and use human power where it counts. So what other problems did we run into? Well, the week before we actually made the switch, we had it planned, and we had 2 network links running across the country, 2 different providers. They can fail. So we actually had them both fail on the exact same day, about 2 hours apart. One was a line card failure, one was one of the fiber lines got cut by a bulldozer. So even if you have redundancy, your network links can fail. In that case, we had to postpone our move because, well, we ran into a rare scenario, but those happen. Elasticache performance was another problem we ran into. We had some difficulty trying to figure out what exactly was going on there. Elasticache is mostly a black box. You get some CloudWatch metrics. Eventually, we discovered the bug along with the help of some of the Elasticache engineers. So it's very useful to get them involved. They're very helpful. But this is just an example of sometimes your change might not work, and you'll have to run your own. In our case, it was Memcache. Currently, that's working out fine for us, but I just wanted to mention that the Elasticache team is working really well with us to improve the quality of the product. Another tool we found very useful for handling problems, discovering performance problems on the fly, was New Relic. So we really recommend using this or some other APM product. So what did our change look like in terms of performance? So I have a couple graphs here, and I'll explain them to you. The first one on top here, so this is our average response time, and the day we made the change was 5:17 on this graph, roughly around midnight. And you can see previous to that, you get very, very inconsistent latency. Post-change, it's nearly smooth. Around, let's see. So post-move, we were roughly around 100 milliseconds on average in latency. Previous to that, we were more in the 200 millisecond range, and we've actually gotten that down to 50 milliseconds. So in terms of web performance, 50 milliseconds, that's great, but what we're, on the ops side, we're really impressed by the consistency of the performance. The second graph here is a graph of our photo serving latency. So this is something we previously had to make. We often had to make cross-country checks, and this is a really expected results because we got rid of some of that cross-country traffic, which adds about 70 milliseconds to your communication. So we see the photo serving latency going down basically to whatever S3 can provide. And here are a couple, as the person who runs our databases, this is what I found most impressive was a couple of our certain queries that we run previously were very poor performing, and as you can see in the first graph, the blue line is the actual response time. Wow, look at that. That's like 10 times better, going from 20 milliseconds down to 2 milliseconds. And the second chart there. So part of it was just an increase in, so there were a lot of little tricky things with our SSDs that I didn't exactly know the cause. So it's a little fuzzy there for me. But what I really was impressed by was just the consistency of the performance on the high 1.4 extra large. This one was, I just picked it out because it was the one that really showed what you can get out of the high 1.4 extra larges. And finally, on the bottom here, so this is a graph of our traffic from the Google bot. And one of the, maybe something you wouldn't expect is that Googlebot really likes fast sites. So what we found is, wow, we switched over, our site got way faster, and then Google sends us twice as much traffic, which is really great because all of our customers like getting more bot traffic. You know, their search rankings go up, and they really appreciate that. Their site gets crawled more often. So back when we were in the data center, our performance fluctuated during the day. It's because we couldn't over-provision for every day. We always have large peaks, especially early in the week. So we'd have some fluctuating performance. We'd have great performance at night and somewhat slower performance during the day. With AWS with scaling, we had flat performance through the day, as you saw in the previous charts. And that was just removing all these scalability limits that we had before. So networking was a really key improvement, having all your instances distributed in an AZ. So if you think about most people's network architecture, you know, you have a very strict architecture in a data center. Everything goes through, you know, a rack switch and into a router. And that's good in some ways. You have good control over your latency. But what AWS offers is you just get some random instance. Who knows what switch it's on? You don't really mind. So you lose a little in latency, but where it really pays off is in consistency. You never run out of bandwidth. Well, you do, but you don't run out of aggregate bandwidth. What we found actually in a recent test was we are moving some data across Amazon's network exclusively, and we were doing 50 gigabytes a second across the country. Wow, you know, how can you do this on your own? Can you rent a connection like that? Not really. So for moving large amounts of traffic, for traffic like a website, AWS is perfect. There's a lot of talk about latency and consistency, but we think the trade-off on throughput is worth it. And success here meant that we could go out on, let's see, May 18th the next day and go watch Star Trek. And there it is. That was success. So what did we learn? I said that SmugMug loved AWS before, and we love it even more now because we're 100% in. That's 0 data centers to manage. Automating everything was a big key to our move. Previously, we had our old systems which weren't completely managed, and they were done through bits of legacy. Automating them made it easy and was necessary if you wanted to do proper scaling. Understanding some of the underlying details of AWS services is critical. So first of all, understanding EBS is something that when you get started on EBS, you look at it and sometimes you don't think about what it actually is since it works so transparently. You have a disk based on it, but we like to think of it as network-based storage. We know the advantages and disadvantages of that. If you compare it, if you think of it like as some storage appliance, that's sort of a good way to think about it. Although we think it's way better than that. It still has the disadvantages of network storage. You have network problems, and you're going to have some problems with network storage. And historically, we've seen that in action. So some of the other details that we care about in particular are, we have some service. We don't know exactly what's behind it, but we see what happens when different services go down, so we understand what actually depends on what. So for example, we know that previously the elastic load balancers would always have trouble when EBS did, and now they don't. So that's something we really wanted out of AWS that we requested. Unpredictable ops schedule. So your ops team probably has a lot on their plate. They probably have a very inconsistent workload. You're either troubleshooting, firefighting, and how do you schedule something for an ops team like that? Well, you can. You just have to make room for the project and accept a little bit of lateness. And it works out. And the number one lesson I took out of this was, what's our job? Well, our job is really to make business happen. Our job is the same as our developers. Our job is the same as operations. It's the same as marketing. It's the same as our CEO. We make the business happen. So that's really our goal. It's the same goal as everyone else. Our job isn't to run data centers. It's not even to run AWS. Our goal is to make the business happen. So we made some more changes because, well, we could. Why not? Well, I can talk about some of the advantages and disadvantages. We're moving our infrastructure, so why not rebuild it? Sure. Previously, we were running old versions of Linux and MySQL, so we upgraded all that, installed some new monitoring tools. We got rid of some of our NFS dependencies, moving them to S3 and Dynamo. And some of our code pushes previously were just pushed out on an NFS server, not very well distributed and a single point of failure. Although we switched it to using something that we completely rely on, which is Amazon S3, very high availability, and used an internal torrent to distribute our code. So one last thing I want to talk about here is we went multi-AZ. Well, wow, great. What does that mean? So multi-AZ is much easier than going multi-data center because going multi-data center, you have to manage all these cages, like I mentioned before, 3 times as many contracts, on and on with the data center setup. Multi-AZ, on the other hand, it's really as simple as just making sure your AWS resources are in the right place. So the way we have it set up is we have our load balancers, our ELBs, sending traffic to redundant HA proxy clusters per AZ. And then in each AZ, we have a group of web clusters and DB replicas. In our HA proxy configurations, we back up our cluster configurations with cross AZs. So if we have one of our clusters go down in one AZ, the HA proxy will direct traffic to machines and other AZs. And that traffic is actually pretty low priced, although I think it's a pretty high margin product, but it works great for us. And finally, the biggest tip for going multi-AZ is, so almost every infrastructure you end up with single points of failure. In our case, we have, for instance, MySQL running in regular master mode, so that's a single point of failure. And you probably have multiple of them, so keep them all in one AZ. If you have AZ failures, if you have multiple single points of failure and multiple AZs, that exposes you to a lot more failure scenarios. So that's all I have today. And thanks again to our ops team. Thanks to all of you for sticking around to the bitter end here. Again, my name is Andrew-Shieh, and you can contact me here. We have, let's see. Oh, I wanted to announce that we have some job openings at SmugMug's. So if anyone's interested in that, talk to me afterwards. And we have a discount if you're a photographer and interested in having some photo hosting. We have a discount code, reinvent, if you sign up. And again, you can talk to me later.